Welcome to another deep dive. And wow, this time, you folks have really outdone yourselves with the stack of sources. I mean, we've got everything from Zen Buddhism with stuff about Muman and those mind-bending koans to the intricate world of mathematical systems and even some pretty cutting-edge stuff about artificial intelligence.
Yeah, it's a fascinating mix.
It is.
Yeah.
Now, on the surface, these might seem like totally different universes of thought, but trust me, there's some hidden connections here, some really strong undercurrents that tie them together in ways you might not expect.
Definitely.
So we're going to be diving into these core ideas of self-reference, those paradoxes that make your head spin, and the whole idea of levels of abstraction, those mental models we use to make sense of the world. Oh, and then there's this really intriguing idea of how really simple rules can sometimes lead to crazy complexity and outcomes you'd never see coming.
It's going to be a wild ride.
It is. Consider this your personal guided tour through some pretty mind-blowing intellectual territory.
What strikes me right away, even before we get into the formal systems and all that, is the surprising connection between something like Zen Buddhism, especially the teachings of Muman, and his take on koans, those paradoxical riddles designed to, shake you out of your habitual thinking. And then on the other hand, there's the world of mathematical philosophy, which many people see as super rigid and rule-bound. But there's this shared spirit there, this drive to push beyond the limits of our ordinary logic and really grapple with ideas that seem to contradict themselves.
Yeah, absolutely. It's like they're both trying to point to something that lies beyond our usual ways of thinking. And that brings us to a concept that keeps popping up in the material you sent, this idea of strange loops and tangled hierarchies.
Yeah.
To really get a feel for this, let's start with something you can actually hear, a really captivating musical example. It's Bach's Canon per Tonos from the musical offering.
Ah, beautiful choice.
So for anyone out there who isn't a musicologist, this piece has these three interwoven melodies.
Right. They're intricately woven together.
They are. So you have the main melody, which is this really graceful twist on a theme, and then underneath it, there are two more melodies kind of echoing each other in this canonic harmony based on a different musical idea.
And it's what happens with these lower voices that makes the whole thing so unique.
Exactly. The lowest one starts in C minor, which is the main key of the piece, right? And the one above it, it starts on the same melody, but a fifth higher.
What makes it so loop-like, so fascinating in its structure, is what happens at the end, or what you think is the end. You see, instead of resolving back to that home key of C minor, it shifts. It modulates almost sneakily into D minor.
It's like it's playing a little trick on you.
It is, and the brilliance of Bach is that this new ending, it fits perfectly back to the beginning, so you can repeat the whole thing and it'll modulate again, this time from D minor to E minor, and on it goes.
So it's kind of like climbing a staircase, where instead of reaching another floor, it somehow circles back to the ground level, but you're a step higher than where you started.
Exactly. A musical Escher staircase.
And get this, after 6 of these upward key changes, you end up right back in C minor, the original key, but an octave higher. It's amazing. Bach even wrote this little note in the margin. As the modulation rises, so may the king's glory. Which to me hints that this could theoretically go on forever, this upward spiral.
It's mind-boggling when you think about it.
It is. So this feeling of moving through a hierarchy, in this case, it's musical keys, and then bam, you find yourself back where you started. But on a different level, that's the essence of a strange loop. And sometimes these loops can get tangled up with each other, and that's how you get a tangled hierarchy, where the different levels of the system get all mixed up in these unexpected ways.
And this happens all the time in complex systems, not just music.
Right. So you see, even in something as structured and beautiful as music, you have these self-referential patterns where going up can lead you back to the beginning, but transformed. It kind of gives you a taste of how seemingly ordered systems can have these hidden circularities.
And that musical example is a perfect starting point because it's something you can actually experience, hear and feel it. But as we dig into these sources, you'll see this theme of strange loops popping up in some seriously abstract areas, sometimes hiding in plain sight, sometimes disguised in these really clever ways.
Okay, so let's go deeper now and venture into what some might call the Mount Everest of intellectual thought, Gödel's incompleteness theorem. Now, we know just the name can sound a bit intimidating.
Oh, yeah.
But our mission here isn't to get lost in the mathematical weeds.
Definitely not.
We want to get to the heart of it, to those truly revolutionary insights that Gödel uncovered.
Exactly. And at its core, Gödel's work is built on this idea that's incredibly simple to explain but has really profound implications. And that is, statements about numbers, the relationships between them, can actually be represented within the world of numbers itself. And he did this using a technique called Gödel numbering.
Right, so it's like a code, a way to translate statements about math into the language of math itself.
Precisely. And it's really clever. Imagine assigning a unique number to every symbol we use in basic number theory, like the plus sign, the equal sign, the digits 0 through 9, even those parentheses.
Right. And since any statement in number theory is just a string of these symbols, a whole mathematical sentence, no matter how complicated, can also get its own unique number. It's like giving every mathematical statement its own ID card.
Exactly. It's kind of like a universal product code for mathematical statements.
I like that.
No.
And the really cool thing is that this lets you view a statement in two ways. First, there's the normal way we read it as a statement within number theory, talking about how numbers relate to each other.
Right, like 2 plus 2 equals 4.
Exactly. But then, because this number also uniquely identifies the statement itself, you can also see it as a statement about another statement in number theory, or even about itself.
And that's where things get really interesting, where those strange loops start to appear.
It does feel like one of those mind-bending Mobius strips, where inside and outside get all twisted up. And it takes us right to one of the oldest and trickiest logical puzzles, the Epimenides paradox.
You mean the one that goes, this statement is false?
That's the one. It's so simple, but it creates this inescapable logical loop.
It's like a dog chasing its own tail.
And what Gödel did was translate this kind of self-referential idea into the precise language of number theory. Instead of talking about falsehood in general, he crafted this statement that when you decode its Gödel number, basically says, this statement can't be proven true within this particular formal system. And the system he targeted was Principia Mathematica, that massive project by Russell and Whitehead, which was trying to create a completely rigorous foundation for all of mathematics.
Ambitious project, to say the least.
Oh, yeah. But to really get why Gödel's work was so groundbreaking, we need to zoom out for a minute and look at the historical context.
Right, because mathematicians had been on this quest for centuries. They wanted to make reasoning completely foolproof, to create these systems of axioms like self-evident truths and rules of inference, which are like the logical steps you take to prove something. And they wanted to use these to derive every true mathematical statement step by step with absolute certainty.
Thinkers like Boole, De Morgan, Frege, Peano, Hilbert, they were all wrestling with this idea of what makes a mathematical proof truly solid.
And David Hilbert, he had this grand vision.
He did.
He wanted to prove, using only the most basic, intuitively obvious kinds of reasoning, what he called finitistic methods, that a system like Principia Mathematica was both consistent, meaning it couldn't lead to contradictions, and complete, meaning it could, in principle, prove all true statements about numbers.
So Hilbert's dream was basically to create this ultimate rule book for mathematics, right?
Yeah. One that would settle all the questions and leave no room for doubt.
But then along comes Gödel, and he drops this intellectual bombshell. His incompleteness theorem, it basically showed that Hilbert's dream, at least in its purest form, was impossible.
Yeah, it was a real game changer.
He proved that any system of axioms powerful enough to handle basic arithmetic would always be either incomplete, meaning there would be true statements he couldn't prove, or inconsistent, meaning it would contradict itself.
It's like saying you can have a perfect map, but it can't be complete, or it can be complete, but it can't be perfect.
And the second part of his theorem was just as mind-blowing. It said you couldn't even prove the consistency of a system like Principia Mathematica using only the methods within that system itself, unless the system was actually inconsistent.
It's like the system trying to look in a mirror and see its own reflection, but the very act of looking creates a distortion.
Oh, that's a great way to put it. And the irony, as we've been talking about, is that Gödel did this by essentially smuggling the core of that Epimenides paradox, that self-referential loop, right into Principia Mathematica, which was designed to avoid exactly these kinds of logical traps. It didn't destroy the system, but it completely changed how mathematicians thought about the limits of logic.
So Gödel essentially showed us that there will always be true statements that we can't prove within any given formal system. It's like there's always this little bit of mystery that lies just beyond our grasp.
Okay, so now let's talk about decision procedures. Your sources bring this up with examples like the MIU system and the PQ system. So what exactly is a decision procedure? It's basically a foolproof test you can apply to a string of symbols in a formal system.
Right, it's like a set of instructions you can follow, and in a finite amount of time, it'll tell you for sure whether that string is a theorem, meaning it can be logically derived from the system's axioms.
So the rules of a system define what a theorem is, but a decision procedure gives you a way to actually check.
And the checking process will always end. That's the key thing. It won't get stuck in an endless loop.
I see. So for example, in that PQ system we've been talking about, every theorem has this specific form. A bunch of hyphens, then a P, then more hyphens, then a Q, and finally another bunch of hyphens. And the decision procedure is, well, it's super simple. The number of hyphens in the first two groups has to add up to the number of hyphens in the third group.
Exactly. And you can apply that test to any string in the system. Like, let's say you have the string PQ. Well, 2 hyphens plus 1 hyphen equals 3 hyphens, so it's a theorem.
So simple. But then what about the meaning of these symbols? Initially, they're just arbitrary marks, right? They don't inherently mean anything.
Right. It's like looking at hieroglyphics before you know how to read them, just shapes on a page.
But, as one of the sources points out, if you can find what they call an isomorphism, which is basically a deep structural similarity between the theorems of a formal system and true statements in some other domain, well, then you can say those symbols have taken on a kind of meaning.
Right. It's like finding the Rosetta Stone that lets you translate between the formal system and something you already understand. Like in the PQ system, if you let P stand for plus and Q stand for equals, suddenly all those abstract theorems become true addition statements.
Oh, I get it. So it's like a dictionary between a formal system and something meaningful.
Exactly.
But there's a big difference between how meaning works in a formal system and in a natural language, like English.
Oh, yeah, for sure.
In English, when you learn a new word, it can change how you think, how you construct sentences, even the rules of grammar. But formal systems, they've got this fixed set of theorems that are already baked in from the beginning.
Right. Finding an isomorphism doesn't let you add new theorems that weren't already there implicitly. The requirement of formality is all about that fixed, predefined nature of formal systems.
That makes sense. Okay, let's move on to another system that was mentioned in the sources. One designed to represent prime numbers, which they called the PNAC system. What's the big challenge in trying to capture this idea of a prime number using only typographical rules?
The tough part is figuring out how to express this idea of non-divisibility. To say a number is prime, you basically have to say it's not divisible by any whole number between 2 and 1 less than itself. But in a formal system, you can't just wave your hands and say, and so on, or up to this point. You've got to spell it out using the system's symbols and rules. You need a clever way to say this number is divisor-free, but in a purely typographical way.
It's like trying to define something as based on what it's not rather than what it is.
Exactly. It's about finding a way to express absence within a system designed for presence.
I see. And this brings up the whole idea of undefined terms. Just like geometry starts with undefined concepts like point and line, number theory has its own fundamental undefined concept, the natural number.
Right. And it's interesting to compare this to how non-Euclidean geometries came about. You know, when mathematicians started questioning Euclid's fifth postulate about parallel lines, and by changing that postulate, they ended up creating these different but still consistent brands of geometry.
So in number theory, we usually think of piano arithmetic as like the standard version, the one that captures our basic intuitions about numbers. But Gödel's theorem implies that there are actually infinitely many other non-standard number theories that are consistent. So while the variations you get in geometry might be limited, it seems like the world of number theory is much wilder with all these different branches.
Exactly. A real jungle out there.
And this idea of consistency is actually trickier than it might seem. It's not some absolute property of a system. It depends on how you interpret the symbols. Like in that modified PQ system we talked about, if you change what Q means from equals to greater than or equal to, it can completely mess up the system's consistency and completeness.
A looser interpretation might give you consistency but make the system incomplete, while a stricter interpretation can sometimes make it both consistent and complete. It's about finding the right balance, the interpretation that fits best.
Okay, let's shift gears for a bit and talk about those recursively transition networks, or RTNs, that were mentioned in the sources. How do these connect to the ideas of hierarchy and self-reference we've been discussing?
RTNs are basically a way to formally describe the structure of things, like, for example, how noun phrases are put together in English. The key idea is this concept of procedure calls, where one network can temporarily jump to another network to do a specific job and then return to where it left off. It's like calling a subroutine in a computer program.
So it's kind of like delegating a task.
Exactly. So imagine you have an ornate noun network. It might call an article network to get the or a, then it might call an adjective network to get something like big or red, and then finally it calls a noun network to get a word like dog or house.
So you get this layered structure with all these calls and returns, kind of like those tangled hierarchies we've been talking about.
Right. The different levels of the system can interact in these really complex ways.
This makes me think about the different ways we can interact with these formal systems. There's what the source calls mechanic mode or M mode, and then there's intelligent mode or I mode, and even this more intuitive Zen-like Un mode. Can you walk us through these?
Sure. So in M mode, you're basically treating the system like a game. You're moving symbols around according to the rules, but you're not necessarily thinking about what they mean. It's like playing chess without caring about strategy, just moving the pieces based on the allowed moves.
So it's like focusing on the syntax without worrying about the semantic.
Exactly. Now, I mode is all about interpretation. You're trying to understand what the symbols and theorems mean, how they relate to something outside the system, to your own knowledge.
So it's like playing chess with an understanding of the game's strategy and tactics, not just the rules.
Right, you're trying to see the bigger picture, the deeper patterns. And then there's the unmode, which is harder to pin down. It hints at a more direct way of engaging with the system, maybe through intuition or pattern recognition that goes beyond explicit rules and interpretation. It's more like a Zen master's approach to the game, seeing the board with a kind of intuitive understanding.
I like that. Now, one of the most mind-blowing concepts that comes up in these sources is the diagonal argument, which actually has deep connections to Cantor's work on infinity. Can you give us the gist of it?
So the diagonal argument is this really powerful technique that reveals this weird kind of self-reference that often pops up when you're dealing with infinite sets. Imagine trying to make a complete list of all the real numbers between 0 and 1, all those decimals that go on forever.
So like 0.1, 0.11, 0.111, and so on.
Well, not exactly, because those are just repeating decimals. The real numbers include all the non-repeating ones too, like pi and the square root of 2. Anyway, the diagonal argument shows that no matter how hard you try, no matter how comprehensive your list seems, you can always create a new real number between 0 and one that's not on your list.
How do you do that? It sounds impossible.
It's actually quite elegant. You look at the digits along the diagonal of your attempted list, the first digit of the first number, the second digit of the second number, and so on. Then you change each of these digits, creating a new number that differs from every number on your list in at least one decimal place. This proves that your original list was incomplete, that you can't capture all the real numbers between 0 and 1 in a list like that.
So even though you're trying to be comprehensive, this self-referential trickery shows that you'll always miss something.
It's like the universe of real numbers is always one step ahead of you.
That's wild. And this feels connected to the idea of quiening, which was also mentioned. These are sentences or computer programs that can somehow output their own source code. It's another form of self-reference, but as the source points out, it's not always as simple as just telling a program to print this exact sentence.
Right. Quiening often involves these clever, indirect methods where a program uses its own code as data to construct its output. It's like a snake swallowing its own tail, but in the world of computer programs.
Okay, back to Gödel. The source mentions proof pairs in the context of TNT, which stands for typographical number theory, the formal system built on Principia Mathematica. How do proof pairs tie into this idea of self-reference?
It's about representing the relationship between a proof and the statement it proves within the system itself. Think of it like this. A proof pair is like having a recipe that's the proof and the finished dish, which is the theorem.
I like that analogy.
So Gödel figured out how to talk about the relationship between the recipe and the dish using the language of cooking itself. He realized that a statement like MU is a theorem, and this is just a simple example from the MIU system, could be translated into a statement about numbers and proof pairs within TNT.
So you're essentially encoding the idea of a proof within the system itself.
Exactly. A proof pair consists of a series of steps, the formal proof and the final statement that those steps lead to the theorem. And Gödel found a way to link a statement's Gödel number with the Gödel number of its proof, using only the vocabulary of number theory.
And that was the key that allowed him to construct that famous Gödel sentence, right?
You got it. The sentence, usually represented as G, that essentially says, I am not provable within TNT.
It's mind-blowing how he managed to do that.
It really is. And the source then talks about what happens if you try to outsmart Gödel by adding his sentence, G, as a new axiom to TNT, creating a new system called TNT plus G.
Yeah, it seems like it wouldn't work, right?
Exactly, because you can just use the same kind of Gödel-like construction to come up with a new statement, G, that this new system still can't prove. It's like this endless game of whack-a-mole, where every time you patch a hole, a new one pops up.
So you get these bifurcations in number theory where new truths are always emerging just beyond the reach of the current system, really highlighting the fundamental incompleteness Gödel discovered.
Exactly. And the source even mentions this hypothetical omega axiom for TNT plus G, which would represent an infinite set of axioms based on G, hinting at the incredible depth of this incompleteness. It's like saying there are infinitely many layers to this onion, and you can keep peeling them forever.
So this has some pretty big philosophical implications, doesn't it? The source brings up Lucas's argument, which claims that Gödel's theorem actually disproves mechanism, the idea that our minds are just machines or algorithms. Lucas says that we can understand the truth of Gödel's sentence even though the system it refers to can't prove it, and that this is something a purely mechanical system, like a computer, could never do.
Right. Lucas argues that any program designed to generate theorems will always miss its own Gödel sentence, while a human mind can see its truth. It's a pretty bold claim, and it really gets to the heart of what it means to be intelligent, to have consciousness.
Yeah, it's a really deep question. And to connect this back to computers, the source explains how you can apply Gödel numbering to the MIU system too. By assigning numbers to the symbols M, I, and U, and to the rules for manipulating them, you can turn problems about the MIU system into problems about numbers.
Right. It shows that the rules for manipulating symbols can be mirrored by arithmetical rules on their Gödel numbers. This isomorphism lets you study formal systems using the tools of mathematics. It's like having a powerful new lens to examine the nature of these logical systems.
This all makes me think about the idea of levels of description, which the source illustrates with this really interesting example of a chess game. They talk about how a novice sees the game compared to a chess master. What can this tell us about understanding complex systems? I mean, think about your own area of expertise. As you become more skilled, you probably see things that a beginner would completely miss.
Absolutely. A beginner sees the chessboard as just a bunch of individual pieces on squares. They might focus on one piece at a time, thinking about its next move, but a master sees the board in chunks. Recurring patterns, relationships between groups of pieces, strategic structures that might span many moves. They're playing the game on a different level.
So they've developed this ability to see the bigger picture, to operate at a higher level of abstraction.
Exactly. And this applies to all kinds of complex systems. Experts in any field, they learn to see patterns and connections that are invisible to someone just starting out.
This reminds me of nearly decomposable systems, which are discussed in the sources. These are systems made up of modules that interact in a somewhat loose way, so the modules can still behave independently while also contributing to the whole system.
Oh yeah, like an atom. The nucleus and the electrons, they have their own thing going on, but they also work together to create the atom as a whole.
Exactly. So these systems often have this hierarchical structure where things at one level are made up of things at a lower level. But the interesting part is that the interactions between levels are usually weaker than the interactions within a level. And this kind of modularity, this separation, it makes it easier to understand these really complex systems because you can study them piece by piece, level by level.
Right. It's like breaking down a complex problem into more manageable chunks.
Now, there's this saying that gets thrown around a lot when people talk about artificial intelligence. Computers can only do what you tell them to do. But the sources take a more nuanced view of this. What's their main point?
Well, on one level, that saying is true. A computer is just executing instructions. But the thing is, real software can be so incredibly complex, with millions of lines of code all interacting with each other and with the data they're processing. And that can lead to what they call emergent behavior, outcomes that are really unpredictable, even for the programmer who wrote the original code.
So even though the underlying rules are fixed, the consequences can be surprising, almost like watching a natural phenomenon unfold.
Exactly. And this connects to the fact that progress in AI has been really tightly linked with the development of these new, more abstract computer languages.
And how have these new languages helped advance AI?
Well, these higher level languages let programmers express really complex ideas and operations more intuitively. They allow you to think and code at a level that's closer to how humans think, instead of having to deal with all the nitty-gritty details of machine code.
So while you could theoretically do everything in machine language, it would be insanely difficult and time-consuming. These new languages are like giving AI researchers much better tools to design and build intelligent systems. And that leads us to what the source calls the AI thesis. What is that all about?
The AI thesis basically says that as AI gets more sophisticated, the mechanisms behind it will start to resemble the mechanisms of human intelligence. It suggests that there might be some fundamental principles of intelligence, and that both biological brains and super advanced AI will eventually converge on these principles as they get smarter.
So it's like saying intelligence is intelligence, whether it's running on neurons or silicon.
Exactly.
And then there are those other really important limitative results mentioned in the sources, like Church's theorem and Tarski's theorem. What do those tell us about the limits of formal systems in computation?
Church's theorem basically says that there's no universal method, no algorithm or decision procedure that can tell you for sure whether any given statement is a theorem within any formal system that can handle arithmetic, like Gödel's TNT. And Tarski's theorem, it's about truth, and it says that you can't have a formal system that contains a complete and consistent definition of its own truth.
So together, they tell us there are fundamental limits to what could be decided, proven, or even fully defined within these logical systems.
Right, it's like there are these ultimate boundaries to what we can know and express within the world of formal systems.
And then there's the famous Turing test, which was also mentioned as a way to judge the intelligence of a machine. Remind us how that works.
The Turing test says that if a human can't tell whether they're talking to another human or a machine in a natural conversation, then we should consider that machine to be intelligent. It's all about behavior, about whether a machine can pass for human in a conversation.
So it's like a duck test for AI.
Exactly. If it looks like a duck, swims like a duck, and quacks like a duck, then it's probably a duck. Or in this case, intelligent.
Okay, and then the source talks about this early AI program called SHRDLU, which took a different approach to understanding language. What was unique about SHRDLU?
SHRDLU was really groundbreaking because it combined different aspects of language understanding, like parsing sentences, reasoning about a simplified world made of blocks, and answering questions about that world.
So it wasn't just focused on one narrow task.
Exactly. Unlike many other programs at the time, which tried to break down language into separate modules, SHRDLU really integrated these functions.
And it did this using what they call a procedural representation of knowledge, right?
Right, which challenged the idea that you could just build AI by developing these separate modules and then plugging them together.
And finally, the source explains how AI programs can use concept networks, sometimes called semantic nets, to represent knowledge. How do these work?
Concept networks are basically like maps of ideas. They show the relationships between different terms and concepts, like what's similar to what's part of what are the properties of things, and so on. When the program encounters a problem, certain concepts in the network get activated, and then the program can use the connections in the network to find information, make inferences, and come up with solutions.
So it's like the program is navigating a network of ideas.
Exactly. And the source also mentions meta descriptions, which are like descriptions of descriptions, as a way for these programs to find patterns and make generalizations at higher levels of abstraction.
So it's like they're building their own mental models of the world, just like we do.
Right. It's all about finding ways for AI to learn and reason at a more abstract level.
Wow, so we've covered a lot of ground in this deep dive. We started with strange loops in music, then went through Gödel's mind-blowing incompleteness theorem, which showed us the inherent limits of formal systems. We explored how meaning emerges in these systems and in language, and we even touched on the ongoing quest to understand intelligence and create AI.
And through it all, we've seen how these seemingly simple rules and concepts can lead to profound and unexpected insights, really connecting mathematics, computation, and even our own thinking in surprising ways.
Absolutely. And this leads us to a final question for you, our listener. Given the limitations Gödel uncovered, how do you think our understanding of truth and knowledge will need to change in a future increasingly shaped by AI, which might run into those same fundamental limits?
It's something to really ponder.
Or think about this. If these self-referential loops and tangled hierarchies are not just curiosities of logic but are actually built into both formal systems and our own minds, what might that mean for how we approach complex problems in any field? It's a question worth exploring. And that's it for this deep dive. We hope you found it as stimulating and thought-provoking as we did.
We just scratched the surface of these topics. There's so much more to explore.
So, until next time, keep thinking, keep questioning, and keep exploring.
And keep sending us those amazing sources.
Absolutely. We love seeing what you're all thinking about.